Okay, so welcome back to this second lecture of model second, motion in the central force field. In the last time we discussed the central force, what is the central force and what is the nature of the central force, which is different from the rest of the forces. Okay, so it is only depends on the r coordinates and not the theta and phi dependence of the central force. Okay, so let's move to the next part, that is the equivalent one body problem. So if you have a system which is made up of this n number of the particle, so in the first module we see that this sum of these all the n number of particles we can represent with the single one body problem, with the single one body by assigning the certain laws of the physics. Okay, so in the same case in the central force field we again derive this, what is the equivalent one body problem if you have more than one particles. Okay, how to represent such kinds of the system by the single, because why we are representing this equivalent one body problem, why we need these equivalent one body problem, because if we consider the more than one particle in a single system, so in that case it is very tedious problem to solve such kinds of the applications, such kinds of the motion of the particles, because each particle has its own motion independent on the rest of the particle. So it is easier way to construct the system which again assigned to the single particle. Okay, so the collection of those particles can be represented by the single particle. So it is again quite interesting topic. It is again quite important as far as the system where the more than one particle is present. Okay, so let us look at what is the equivalent one body problem, or what are the different applications of this equivalent one body problem. Okay, so let's start. Suppose if you have a mass m1, this is point mass m1, and again second mass m2. So we are considering the two masses, mass m1, and we are considering the some point O, that is the reference point or reference origin we can say. So the position vector of this point m1 be the, let's say r1 be the position vector of this mass m1 or first particle with respect to origin O. You can choose origin anywhere, you can choose over here, over here, over here, so it's up to you. So O be the point, we can say reference point or the origin. Second point, that is the mass m2, particle second, whose position vector is r2, where r1 and r1 bar and r2 bar be the position vector of particle 1 and 2 respectively. Of course, particle having masses m1 and m2. Okay, so this is two mass system, and how to represent this mass with the single one mass or center of mass. So how to calculate the center of mass? So it is a mass through which, if you consider the m1 and m2 be the system which consisting these two masses m1 and m2. So how to find the center of mass? Center of mass is the total mass of the system which is supposed to be concentrated at a certain point. If we consider the system consisting of these two masses m1 and m2, so the center of mass of this whole system is the point where whole mass of the body is supposed to be concentrated. Suppose if I choose the middle of this, not exactly middle but in between the m1 and m2, I choose the point where the mass or the center of mass supposed to be concentrated. Okay, and the position vector of the center of mass is, let's say, r. Okay, so center of mass is the mass n between mass m1 and m2. Okay, so if you have a n again more than one particle, again you can choose the center of mass by making a arrangement. So the point where whole mass of the body is supposed to be concentrated. Okay, in our case we have these two masses, mass m1 and m2, and combining these two masses we have a point where whole mass of body is supposed to be concentrated, and this point we denoted as a cm, center of mass, and the r bar be the position vector of the center of mass with respect to origin O. Okay, so the how to write this center of mass coordinates or origin position vector of center of mass. So position vector of center of mass is, yes, from the last lecture. So r bar is equal to, yes, m1 r1 bar plus m2 r2 bar upon m1 plus m2. So this is already known. Okay, so this is the position vector r, and we know this from the last module, we can say last topic of the last module. So this is a position vector of center of mass with respect to origin O. Okay, so this is r bar, and r bar can be written in terms of the masses of the system which constitute the whole system. Okay, so this is r. So how to write the position vector of first particle or particle first with respect to or respective to particle 2 is, okay, so position vector of particle first with respect to particle 2. Since these r1 and r2 bar are the position vector of m1 and m2 with respect to origin O. But suppose if I want to find the position vector of particle 1, that is m1, with respect to particle 2 is this distance. Okay, this distance or this vector denote the position vector of particle 1 with respect to particle 2. And how to determine this? From the basic vector addition. Since we made this triangle and direction is like this. So this is r1 bar, this is r2 bar, and this is r bar, we can say. So how to find this r bar? Position vector of particle first with respect to second. So in that case we consider this position of m2 as a origin. So with respect to m2, what is the position of m1? We denote it as a r with the position vector of particle first with respect to particle second. And from the basic vector calculus, how to denote this? r2 plus r is equal to r1. Okay, so we can directly write this as, yes, r2 bar plus r bar is equal to r1 bar. So r bar is equal to r1 bar minus r2 bar. This is equation number 2. So remember this, how we can write this r position vector of particle first with respect to second, considering m2 with the origin, and with respect to m2, what is the position of m1? So if we consider m2 as an origin, so by assigning the direction of this r1, r2 and r, we can easily calculate the r value by the basic vector calculus. Okay, so this is equation number 2, but again I can represent those coordinates with respect to center of mass system. Suppose r1 bar prime and r2 bar prime unit vector or the position vector, we can say. Okay, position vector of particle 1 and 2 with respect to center of mass. Suppose if I have this r1 prime, so since those are the r1, r2 bar, we are writing r1 prime and r2 prime be the position vector with respect to center of mass. So in that case we have to consider the center of mass as origin, and from that origin, what is the position of first particle, what is the position of second particle. So if I assign this center of mass as origin or as a reference point, so with respect to center of mass, what is the position of first particle and what is the position of second particle. Okay, so with respect to center of mass, this r1 bar is this r1 prime bar, and from these, with respect to center of mass, position vector of this second particle be the r2 prime bar. Okay, so clear. So in the first case we assign the O as an origin. With respect to O, we assign the position vector of first and second particle. Secondly, position vector of first particle with respect to second. In that case, we consider the reference point as a second for describing the position of first particle with respect to second. After that, we assign the center of mass at a certain point in between the mass m1 and m2, and with respect to that center of mass, what is the position vector of first particle and second particle? So r1 prime bar and r2 prime bar be the position vector of these first particle and second particle with respect to center of mass. Okay, so we are changing just a reference point. We are changing with the starting point, and from the starting point we can assign the several values for these position vector. Okay, so again, how to write this equation 2? If you have this r1 value bar, r1 bar and r2 bar, yes, r bar is equal to, instead of r1 bar, this is r1 bar, this is r1 prime bar. So from the vector calculus, how to know? This is triangle, this r bar plus r1 prime bar is equal to r1 bar. So r1 bar, instead of r1 bar, I just write r bar plus r1 prime bar plus r1 prime bar. This is r1 bar, and similarly for r2 bar, this plus this is again this r2. So minus r plus these r2 prime bar. Okay, so these r coolly cancel out, and again r1 prime bar minus r2 prime bar. Okay, again this equation number 3. Okay, so we have this equation number 1, equation number 2 and equation number 3. Okay, so from the equation, how to write this equation first? Again, yes, how to write this equation? Again, if I just write this separately, m1 upon m1 plus m2, this is r1 bar, plus m2 upon m1 plus m2 r2 bar. Okay, so this is equation number, by the way. Okay, so if we consider the equation number 1 and equation number 2, we make a certain arrangement so that we can represent these r in terms of the single masses. Okay, so multiply equation 2 by m2 upon m1 plus m2. So if you multiply equation number 2 with m2 upon m1 plus m2 value, so how to write this equation 2? Yes, m2 upon m1 plus m2 into r bar, again m2 upon m1 plus m2, this is r1 bar, minus m2 upon m1 plus m2 r2 bar. Okay, so we got this equation, and look at these two equations. We have m2 upon m1 plus m2 r2. In the equation first, we again have this m2 upon m1 plus m2 into r2. So we can easily eliminate the second term from these two equations. So this equation number, let's say equation number 4. Okay, so adding equation number, add 1 and 4. So if you add equation number 1, and so r bar is equal to m1 upon m1 plus m2 r1 bar plus m2 upon m1 plus m2 again r2 bar, and similarly for the equation number 4. So we have to just add this equation. So m2 upon m1 plus m2 r bar, so it's just r bar, is equal to m2 upon this same term, these r1 bar minus of the second term m2 upon m1 plus m2 r2. So we are adding these two terms. So look at these values. So which value is supposed to be cancelled out? So these two terms are fully cancelled out. So what are the remaining terms? So we have this r plus m2 upon m1 plus m2 r bar is equal to, so we have this only this term, so m1 plus m2 plus m1 r1 bar plus m2 upon m1 plus m2 again r1. So we have this r1 bar is common, so common, take it as a common and represent the equation. So r bar plus this m2 upon m1 plus m2 r bar is equal to, if you take common r1, so we'll get this is equal to r bar, r1 bar, sorry. So m1 plus m2, m1 upon m1 plus m2 plus m2 upon, so bases are same, so just add the numerator part. So r1 bar m1 plus m2 again m1 plus m2, so again, so it only r1 bar. Okay, so how to write this? R or r1 bar? R1 bar is equal to r bar plus m2 upon m1 plus m2 into r bar. This is equation number 5. Okay, so this is for r1. So if you substitute the value of r1 in any of equation 1 or equation 4, we'll get the value for r2. So if you substitute the value of r1 in equation number 4, we'll get the value for r2, and I directly write, you can again solve this equation. So similarly r2 bar is again can be written as r bar minus m1 upon m1 into r bar. Okay, so this is again equation number 6. So we have this r1 bar and r2 bar in terms of the center of masses and its own masses. Okay, so we just eliminate those r1 prime and r2 prime. So this is r1 bar, this is a position vector of particle first, can be represented in terms of the center of mass system or the coordinates of the center of mass. So with the help of these center of mass coordinates, we can find the position vector of each and every particle. Okay, so similarly for r2 again. Suppose external force acting on this particle system of two particle is Fe. So in that case, how to represent this system of particle, or how to express the equation of motion for these two different particles. So suppose Fe be the external force acting on the system. So this again, the Fe again can be written as, E stands for external forces, so F1E plus F2E, again this is equation number 6. So this total external force acting on the system of these two particles is the external force acting on the first particle plus external force acting on the second particle. Okay, so those are the two forces acting on the system of the particle. So how to write the equation of motion? Equation of motion is the second law of equation, mass into velocity is equal to forces, and again these forces are two forces, external force and internal force. So again rewriting this equation, so equation of motion for the system of particles. So equation of motion. So we can independently write equation of motion for particle first. So m1 d2 r1 bar by dt square plus f1 external, again it is up to this is okay. No, we have to again look at into the what are the internal forces acting on this particle. Since we have these two particles, so the force should be acting on this first particle due to second, and similarly on the second due to this first. So internal forces should be again considered here. Okay, so plus f1 2 internal, or you can just write the I suffix over here. Okay, so f1 2 and f1e. So similarly for m2 d2 r2 bar by dt square, again f2 external plus f21 internal. So what is f12? Internal force on the first particle due to second particle, and f21 be the internal force on the second particle due to first particle. So where f12 is the I internal force acting on particle first due to particle 2, and similarly f21 again f21 I is again internal force acting on this particle due to particle 1. Okay, so those two forces are equal in magnitude but opposite in the direction. Okay, so this f1 to be the internal force acting on the first particle due to second, and f21 be the internal force acting on the second particle due to first particle. Okay, so this is equation number, let's say this is equation number, this combining these two equations, so sorry, this is equation number 7, this equation number 8. So combinedly, if we represent the system by the center of mass instead of these two systems, if we represent this by this combining these two system of the particle m1 and m2 instead of this m1 and m2, if we represent the total mass of the system as a m, and we can write this equation of motion for that mass. How to write this equation? So equation of motion for equivalent mass or single mass as m d2 r bar by dt square is equal to f external. Okay, so did you remember? So why I am writing these only f external? In the last module we discussed internal forces are eliminated when we consider the Newton's laws of motion. Okay, so if we combining these two equation, or if we combining these two masses, we make the mass m, which is a single body, and this r be the position vector of this center of mass. So in that case internal forces should be eliminated, then and then you can apply the Newton's law. So this is the equation of motion for the equivalent one body problem. Okay, so where this capital M be the m1 plus m2. So you should discriminate these two equations. So since we are writing this equation by considering there is interaction between these two masses between m1 and m2, so that's why we are writing. But we already talked about this total system of the masses. So in that case f external only into the consideration. Okay, suppose if we multiply 7 by m2 and 8 by m1 and subtract. Okay, so we want to multiply equation number 7 by m2. So equation look like m1 m2 d2 r1 bar by dt square is equal to m2 f1 external plus m2 f12 internal, and we have to subtract these. So equation number 8 by multiplying m1. So again m1 m2 d2 r2 bar by dt square is equal to m1 f2 external plus m1 f21 internal. Okay, so if you subtract these two equations, what do you get? m1 and m2 both are common, so m1 m2 d2 r1 bar by dt square minus d2 r2 bar by dt square. So this is minus is equal to this m1 n1. So since there is no common term to cancel out, so we directly write this equation. So m2 f1 e minus or plus, we directly write this m2 f12 internal minus m1 f2 external minus m1 f21 internal. Okay, so this is all. Since we can common out this d2 by dt square, okay, so m1 m2, and if I common out d2 by dt square, d2 by dt square, remaining term is r1 bar minus r2 bar is equal to this m2 f1e plus this m2 f12 internal minus m1 f2 external minus m1 f21 internal. Okay, but f12 and f21 are equal in magnitude but opposite in direction. So according to Newton's third law, those are the action reaction forces. According to Newton's third law, f12 internal is equal to minus of, since minus sign indicates it is opposite in the direction, so f21 internal bar. Okay, so instead of f21, I just write this f1 2 bars and rewriting this equation. By the way, what is r1 minus r2 bar? Is equal to r bar. Okay, so if you substitute all those values in the above equation look like this m1. So I just write this equation over here. So m1 m2 d2 r bar by dt square is equal to m2 f1 external bar plus m2 f12 internal plus minus m1 f2 external minus and these minus again become plus m1 f12 internal. So f12 common out, so only remaining term is m1 plus m2 f12 internal plus m2 f1 external plus minus m1 f2 external. This is equation number, let's say 10 or 11, so whatever the equation. So divide equation 10, divide equation 10 by m1 plus m2. So if we divide both sides of the equation by m1 and m2, so what is the form of the equation? So let us try to write this. So m1 plus m2 upon m1 into m2 upon m1 plus m2 d2 r bar by dt square is equal to this m1 plus m2 and this m1 plus m2. So it is again coolly cancel out. So f1 2 bar internal plus m2 upon m1 plus m2 f1e plus minus m1 upon m1 plus m2 f2 external. So if you represent, this quantity m1 m2 upon m1 plus m2, it is reduced mass. Okay, so suppose m1 into m2 is equal to m1 plus m2. It is represented by this mu be the reduced mass of the system. And how to write in general, how to write this mu? So if we more than one particle, so mu can be represented this 1 upon mu 1 upon m1 1 upon m2. Okay, so this is the reduced mass of the system. So if we instead of this m1 m2 upon m1 plus m2 we put the value of mu, so our equation is look like this: mu d2 r bar by dt square is equal to this f12 internal plus. So instead, if you want to write this equation m2 upon m1 plus m2 instead of in terms of the mu, we have to multiply and divide this equation by m1. So if you divide and multiply this by m1, so this is again m1 divided by m1. So in order to nullify the effect, and what is this quantity? This is mu. So this equation can be written as this mu upon m1 f1 external minus similarly multiply and divide by m2. So this mu upon m2 f2 external. So common out this mu from the both side. So if you common out d2 r bar by dt square f12 internal bar plus mu is common, so 1 upon m1 f1 external plus minus 1 upon f2 external. So this equation number, let's say equation number 11 or 12. So next equation you can write over here. So look at this f1 m1 f2 m2. Suppose the forces acting on the system are such that which produce the acceleration which is proportional to the m. So suppose f1e is equal to f2e r0. So these terms goes out. Okay, and if this term goes out, so how to write this equation? So these total term coolly cancel out and it comes out to be 0. So in that case, or forces acting on the system which produces acceleration which proportional to masses. So how to write this? Since this force acting on the system comes out to be 0, or those forces are proportional to their masses, so in that case this equation are look like this, since F1e are proportional to M1 and this F2e are proportional to M2. So how to write this equation? F1e bar upon M1 is equal to F2e upon this M2. So this is important result, this equation number 12. Okay, so the forces acting on the system of the particle, let's say F1 and F2, are such that which produces the acceleration, and these forces are proportional to the masses. Since the forces acting on this F1 and F2 proportional in a such a way that they produce the same acceleration. Since the acceleration are same, since the ratio of this F1 and F2, F2 and M1 again same. Okay, so the forces acting on this system is 0, or the forces acting on the system of these two particles are in a such a way that it produces the acceleration which is in the same magnitude, since in that case the forces are proportional to their masses, and we can write this equation as it is. Okay, so F1 upon M2, and again it is the reflection of this Newton's second law of motion. Okay, so we already talked. So if you put the value of 12 in equation number 11, so we can write the equation as, therefore, so equation written as m d2r bar by dt square is equal to F12 bar internal, or this mu r2 bar is equal to F12 internal. Since the equation number 11 or 12 or 13, this is the equation of motion for a single body problem. Since R12 bar, this is the second order derivative with respect to time. So this is the equation of motion, or we can say this is the equation of equivalent one body parameter. So the result of the conclusion of this equation is that we can represent the equation, we can represent the system of particle by assigning the center of mass of the system, or combining the total of system by reducing to the single particle system. So in that case, motion of the particle is dependent on the internal forces acting on the system. So this is all about this equivalent one body problem. So if you have a more than one particle, so in that case the particle or masses of the system can be reduced to the single particle, and in that case the motion of the system of these such particles only depends on the internal forces acting on the system. So this is all about this today's talk. In the next lecture we will again see the next very interesting topic of this orbiting of the system. So again we introduce the Kepler's law of the motion. So this is all about the next lecture. So for today we stop here. Thank you very much.